Okay, so let me go through some history and a bit of reasoning about how to set up this radius, okay? And the discussion is mostly based on Krusky's 2018 article, okay? First of all, we need to base the radius on well-established theory. So if there's some theory or well-established findings indicate that there is a certain range, okay, within which values are equivalent to the value set up in the null, then we can use that range. So first is to turn to well-established theories and empirical research. Also, there's some guidelines provided by authoritative branches, agencies. Let's say for FDA, they recommend ROPE limits of 0.8 and 1.25 for the ratio of means in the two groups. Comparing two means, taking ratio. And contemporary industry standards use ROPE limits around plus minus 20% for application with moderate risk. The ROPE may be narrow, like plus minus 5% to 10% when the risks are high. It is when relatively small effect size is viewed as significant. So we have to, shrink the ROPE for the known value. And the ROPE might be wider, like plus minus 26% to 50% when the risks are low. It is relatively large effect size. It's still viewed as, not that, big of a deal, not that insignificant, not that significant. Okay, so it varies. You can see that. Well, how to decide the radius of the ROPE? Okay, based on Krusky's 2018 article. Well, first of all, let me talk about a concept called effect size. Okay, if you recall, the Newman-Pearsonian approach also proposes the concept of effect size, or emphasizes the concept of effect size, in addition to Fisherian approach to, the frequentist non-hypothesis statistical, significance testing, right? So what is effect size? Effect size, basically, it's a value measuring the strength or magnitude of an effect or an association, okay? So to talk about effect size, I need to cover Cohen's D. Cohen's D is defined as a ratio of, MA, that is the mean in group A minus mean in group B divided by the standard deviation based on, the book by Cohen, published in 1988. And Cohen's D can be converted comfortably to a t-test. And this Cohen's D is called effect size index, for tests of means in standard unit. And here, MA subscript A and M subscript B refer to population means expressed in raw unit, that is original measurement. And sigma is the standard deviation. Its calculation depends on whether the two populations are assumed to have equal variance, right? And then we have different formulas for it. And Cohen defines, D to be small or having small effect. Threshold is 0.2. Okay, so around 0.2 and below it is considered to be, small effect. The median effect size is set at 0.5 and large effect is set at 0.8 for comparing, let's say, in this case, group effect. Okay, group effect. Sawilowski in 2009 revised thresholds to have very small effect. D is equal to 0.001 threshold, okay? Small effect is set at 0.2, medium effect is set at 0.5, large is 0.8, very large is, 1.2, and huge effect is set at 2, okay? Set at 2. Well, given the previous discussion about Cohen's d and thresholds for different effect size, the question remains, again, how to decide the radius of rope. Okay? And here's Krosky's proposal for the rope limits, because, once we set up the rope, then, we can decide pretty much, if the values within a certain range are equivalent of the noun value. Okay, noun value in most cases would be 0. Okay, and Krosky's proposal is largely based on Cohen's d, right? And he proposes that it must be emphasized that half the size of the small effect in this case is 0.1. If you recall, Cohen's d set the effect size to be small at around 0.2, right? So Krosky argues that it must be emphasized that half the size of the small effect, that is 0.1, is merely a fallback convention when there's no way to calibrate effects by their real world consequences. Basically says, well, if there's no well-established theory and empirical evidence, cumulative over time to give us clear idea about the radius of rope, then here we have half the size of a small effect, would be a good starting point. That would imply roughly plus or minus a tenth of standard deviation in Y for 2 standard deviation in X above or below the mean of X. When we talk about, for example, the regression coefficient, and here it basically says, for this computation, standards, performed. And if we standardize X and Y, then the fully standardized coefficient would be, plus or minus 0.05, 0.05. That is, if the standardized coefficient is within this range, that is plus or minus 0.05 away from 0, then we would argue that, the values within that range, okay, is equivalent of the noun, which is 0, Okay? What does that imply? That implies for 2 standard deviation change in X, a change of 0.1 on a scale of standard deviation Y. So all these scales are standardized. It is considered to be trivial. It's considered to be trivial, a small effect equivalent of 0. Equivalent of 0. Yeah? So it is, the range covering 95% of X. Okay. Variation in that range, there is very little variation in Y. So after the stimulus of such huge range change in X, we only get what? 0.1 variation in Y on standardized scale. Then that's considered to be trivial. So here is the decision rule that Krosky came up with for Bayesian assessment of noun values, which combines highest density interval and rope. So according to Krosky on this decision rule, if the 95% highest density interval, okay, that is, overwhelming majority of the distribution posterior falls entirely outside the rope, okay, then we decide to reject the roped value, that is the noun value. Well, not the entire roped interval, but the roped value, In most cases, will be 0, but it does not have to be 0. Well, if the 95% highest density interval falls entirely inside a rope, then we decide to accept the rope value for practical purposes. And people say, what about, not entirely, let's say 50% of 95% highest density interval, it's a false inside rope. Well, then we say, well, undecided. There's not enough evidence from the data that prior can help us decide if we can reject or accept the non-value that's roped. Okay.